Hello everyone, my name is Dr. Matthew Kong and I'll be taking us through this new topic on gas chromatography. Now this topic will be quite different from the previous analytical technique that you have learned, and I'll first describe some principles of chromatography before moving on to the more specific case of gas chromatography. Now chromatography is defined as the separation of components in a sample mixture whereby each of these components distributes differently between two phases. Now this sounds a little bit complex, but I'll explain as the slide progresses. So these two phases in chromatography, typically we call the stationary phase and the mobile phase. Now the mobile phase is typically what allows the sample mixture to move through the instrument, and the stationary phase is the phase that the sample interacts with, and based on the extent of interaction, some chemicals interact more, some chemicals interact less. That will lead us to separation. Now we see this in the picture here, whereby we have a mixture of components in the light blue strip. Now this mixture of components clearly is homogeneous, and we can use chromatography to separate it into its various chemical components. Now as it flows down the strip of paper, clearly its components will interact with the paper differently. So we can see that the dark blue component is starting to interact to a different extent as compared to the black component. The dark blue component is clearly interacting quite a lot more with the paper, and that is why it is being left behind as the sample mixture travels down the paper. The black color component is interacting quite little with the paper, and therefore it is flowing along quite quickly towards the bottom of the strip of paper. So in this case, for the sample mixture here, we call the mobile phase, and the strip of paper we call the stationary phase, because it is the phase that is responsible for the interaction with the various chemical components in the mixture, thereby generating separation. Now this is a schematic of a gas chromatography instrument, and I'll briefly state the three key parts of this instrument before we'll describe this in detail later on in the chapter. So the first key part of this instrument is the gas system here. So this gaseous system acts as the mobile phase, and its sole purpose is to push the sample through the instrument. Now typically the gas used here is some sort of an inert noble gas, so either helium or nitrogen gas, and again its main purpose is to carry the sample through the instrument. So it acts as the mobile phase. In the oven, we see the column. Now the column in a gas chromatography instrument acts as the stationary phase. This is where the various chemical components in the sample mixture is going to be separated. So as the mixture travels through the column, the different chemical components of the sample mixture will start interacting with the column, and of course some will interact more and some will interact less, and therefore the various chemical components will start being separated, very similar to what we saw in the previous slide, and they will therefore leave the column at different times. So right here at the end of the instrument, we see the detector. So the detector's main role clearly is to detect the various chemical components that are passing through the column, and therefore after being separated, we need to see that there are various chemical components that are present in this sample. So these are the three general parts of a gas chromatography instrument, and again we'll describe each of these in a bit more detail as we progress along. Now, when we perform gas chromatography, it's actually quite a simple concept. We take the sample, which is typically in liquid form, and this sample is directly injected into the injector port. So the moment it is injected into the injector port, it is converted from a liquid phase into a gaseous form, right? So it's vaporized and converted into a gaseous form. Then I did mention that the instrument uses a carrier gas, typically helium or nitrogen, to simply carry the vaporized sample gaseous molecules through the instrument, and immediately they will start being passed through the column. So once they are passed through the column, I mentioned that the column is the stationary phase, so that is where separation will definitely occur. So the different components in the sample interact with the mobile phase and stationary phase to different extents. So therefore, some will interact with the stationary phase a bit more, some will interact a little bit less, and they end up being separated before they leave the column. So on the last line here, it actually says that the separation is based on the unique affinities of each component for the stationary phase. So that's just a fancy way of saying that the separation is based on whether each chemical component likes to interact with the stationary phase or not. So of course, some chemical components will really enjoy interacting with the stationary phase, so therefore they will be really left behind and take a long time to pass through the column. And some chemical components will not like to interact with the stationary phase at all, so therefore they would simply flow on through the column very quickly and reach the detector in a very short period of time. So this difference in time that it takes to flow through the column and eventually reach the detector is the core principle behind the separation of these chemical components in the sample mixture. Now, I'll demonstrate this using a picture. Sometimes it helps and it's easier to understand. So as we look at this picture, on the top icon, we see a sample mixture that contains blue gaseous molecules and red gaseous molecules, and you'll see the yellow coating that's on the inside of the GC column that represents the stationary phase that the gaseous molecules are going to interact with. So the column we see as essentially a hollow tube that has an inner coating of sorts, typically some sort of polymer that the gaseous molecules will interact with. So as the red and blue molecules start passing through the column, we see that they start to separate, and this is due to, again, the different extents of interaction with the stationary phase. So in the middle picture, you can clearly see that the red molecules are gradually being left behind, while the blue molecules are actually moving on in front. So this tells us that the red molecules actually have a higher affinity with the stationary phase, or we can say that they prefer to interact with the stationary phase. So therefore, as they're interacting quite a lot, they are slowing down and being left behind in the column. So of course the inverse is also true. The blue molecules do not like to interact with the stationary phase so much, so that's why they are flowing quite quickly along through the column. So in the third picture, we actually see that quite a lot clearer. So the red molecules are clearly already separated from the blue molecules, right? So this, of course, will increase as we go further and further down the column. So right at the end, we see that the blue molecules will leave the column and reach the detector first, and after some time, eventually the red molecules will then leave the column and reach the detector. So just verbalizing some of the things that we talked about in the previous picture. the various components represented by the red molecules and the blue molecules elute at different rates. So elute means to leave the column and to reach the detector, right? And this amount of time that it takes to leave the column and reach the detector is called the retention time. That's the amount of time each component is retained in the column. So we mentioned that components that like to interact with the stationary phase will take a long time to leave the column, so therefore we say that they have a longer retention time. Of course, components that don't like to interact with the stationary phase that much and therefore prefer to flow along with the mobile phase, they will certainly leave the column quite a lot quicker, and therefore we say that they have a much shorter retention time. So at the end of the column, of course, each of these chemical components, it doesn't have to be just 2 chemical components, it can be 3, 4, 10 chemical components. These have to be read by a detector. So the detector will see that a chemical component is leaving the column, and therefore it will generate a peak on the chromatogram so that we know that there is a chemical component present at that point in time with that certain retention time. Now, components in a sample are separated in a column based on their solubility in the stationary phase. Now, this is not a lot different from saying that the various components have preferences in terms of interaction with the stationary phase. So if these components have higher solubility in the stationary phase, then therefore they will interact more with the stationary phase and have a higher retention time. Well, of course, the opposite is also true. If a certain component in the sample mixture has a low solubility in the stationary phase, then therefore this will lead to a shorter retention time. So this is just another way of saying that different components in the sample will interact to different extents with the stationary phase, and that has to do a little bit with their solubility in the particular chosen stationary phase. Now, earlier we mentioned that a detector is positioned at the end of the column, and the detector's main job is to tell us that there is a particular chemical component being eluted from the column at that time. So what the detector does is that it plots something called a chromatogram. Now, a chromatogram is essentially a plot with a bunch of peaks, and each of these peaks will represent one of the various chemical components that are present in the sample mixture. These peaks are shown as a function of time on the x-axis, and this amount of time can actually tell us the retention time. So obviously, if a peak comes out very quickly, it will be towards the left of the x-axis, and if a peak comes out very slowly, it will be more towards the right of the x-axis. So this is an indication of whether the retention time is very small or the retention time is very large. Another thing about the chromatogram is that if we look at the size of the peak, so the area of the peak directly tells us the amount of that particular component in the sample, which means that if we have ethanol in our sample mixture and we see that the peak belonging to ethanol is very huge, then we can understand that there must be a lot of ethanol in that sample mixture. If we see a peak for hexane and the hexane peak is very, very small, then we would get an understanding that there's only a little bit of hexane present in that sample mixture. So the area under the peak or the size of the peak can tell us how much of that particular component is present in the sample. So earlier we mentioned a little bit about the time being on the x-axis. So the time is actually called the retention time, and each component has its own retention time. If ethanol takes 3.5 minutes to pass through the column and reach the detector, then we say that the retention time for ethanol is 3.5 minutes. So the amount of time that any particular component takes to pass through the column and reach the detector, we call the retention time. It is the amount of time that that component is retained in the instrument or in the column. So this is a very simple picture of a chromatogram. We actually see two peaks, one peak to the left, quite a small peak, and one peak to the right, quite a large peak. So these two values, TR subscript A and TR subscript B, actually represent the retention times of component A and component B. So clearly the retention time for component A is much smaller, so therefore it's coming out of the column much faster as compared to component B. We also see from the chromatogram that there's a big difference in the size of peak. Clearly, peak A is much smaller, which means that there's only a little bit of component A present in the sample mixture. But if we look at peak B, clearly it's quite large. So what that means is that there's quite a lot of component B present in the sample mixture. So two important things we can two important pieces of information we can get from the chromatogram would be the retention times of each of these chemical components, and also from the size of the peaks we can understand how much of each of the components are present. Now, as promised earlier, we'll talk in a bit of detail about the various components of a GC instrument. So the first would be an injector. So the injector port, that's where we inject our sample. We mentioned that we have a carrier gas that acts as the mobile phase. Its main purpose is to carry the sample through the instrument. We'll talk quite a bit about the column because that is the most important part of a GC instrument. That is where the separation actually occurs. And finally, we'll bring up three types of detectors that are very commonly used with GC instruments. Now, the injector doesn't serve any purpose except to allow injection of the sample into the GC instrument. So that is its sole purpose, right? The injector port is where we take a syringe and inject our sample, typically in a liquid form, into the GC instrument. So these days, the most common type of injector used is a splitless injector. So these are not two types of injectors. It's the name of this injector is called a splitless injector. So this is just one type of injector. So quite simply, on the right you see a schematic of such an injector. So we have our syringe with our sample in a liquid form, and it's typically injected into this injector port. This injector port is surrounded by a heated metal block that provides heat in order to vaporize the sample into a gaseous form before it's moved on into the column where separation can occur. Now, one thing about this type of splitless injector is that we can control the amount or the fraction of the sample molecules that pass through to the GC instrument. Because a GC instrument is very sensitive, we typically do not require all the sample molecules to go into the column and into the instrument. Typically only a small percentage is required to get very decent results. So this brings us to the concept of a split ratio, whereby if we say that the split ratio is 1/100, it means that only 1% of the sample that has been injected actually makes its way through to the column. The rest of the 99% goes to waste. So for example, if we have a split ratio of 1/10, it means that 10% of the sample that we have injected is going into the column and the instrument, and the other 90% is going to waste. Typically, these are very typical percentages of split ratios that are used, so either 1/100 or 1/10. We very rarely need more than 10% of the sample introduced going into the instrument to produce good results. Most of the time, less than 10% is sufficient. Now, we have mentioned several times that the mobile phase is a chemically inert gas, and there are several options. So we have helium, argon, nitrogen, and hydrogen. But of these, helium and nitrogen are by far the most commonly used, because argon is good, but it's really expensive, right? So cost is one issue. And for hydrogen, of course, we know that hydrogen can react with oxygen to make an explosive mixture. So therefore, typically for safety purposes, we stay away from hydrogen being used as a gas. So that leaves us two of the most common gases used in GC instruments, namely helium and nitrogen. So these two gases can also be purchased quite readily in a very pure form, 99.999%, and can also be purchased in a very dry form. So these are not issues at all. Now, the column is really the heart of any GC instrument, and it's really important to understand how the column functions, and as we explore different types of columns. So one thing about the column is that it is enclosed in an oven that maintains a certain temperature, and the reason for this is because temperature affects the retention time of chemical components. So therefore, if a sample mixture is passing through the column at 150 degrees, and if the same sample mixture passes through the column at 200 degrees, we'll find that the retention times of these chemical components, even though they're the same chemical components, will be different. So therefore, in order to keep the retention times the same so that we can compare, we usually have an oven that controls the temperature of the column. So there are two types of columns. The first is a packed column. So a packed column is really a very old-fashioned type of technology. So we'll briefly talk about what a packed column looks like, but I will also say that the second type of column, a capillary column, is by far the most commonly used type of column in modern chemistry. So these days, very rarely do laboratories use packed columns anymore. So typically we would use capillary columns, and this is because capillary columns produce much better separation of compounds and also require much less volume of sample to analyze. So this is a pictorial representation of a packed column. The concept is quite simple. You have a column. This is a top-down view, and you see that you have circular beads that make up the middle of the column. So as sample is passing through this column, obviously your various chemical components will start interacting with the beads. So the beads are acting as the stationary phase. So as they interact with the beads, obviously some components interact more and some interact less, so therefore separation is generated. So in the very early beginning, we started off with a very conventional packing material, silica beads, and then as technology improved, scientists were able to coat these silica beads with this hair-like silica structure. So you see this hair-like silica structure here, and this improves or increases the surface area with which the various chemical components can interact with. So of course, with greater surface area, this will allow better separation to occur. But of course, as time progressed, technology got better, and that led to the development of capillary columns. Now, capillary columns are significantly more effective in generating separation than packed columns. So over time, scientists or the chemistry community has essentially moved exclusively to the use of capillary columns. Now we'll see that there are two types of capillary columns. The first is wall-coated, and the second is porous layer. Now these two are very similar, and they differ just purely by design. So the wall-coated capillary column essentially has the inner side of the column coated with a polymer. So this polymer is what the various gaseous chemical components will interact with as they are passing through the column, and this generates the separation. For the porous layer capillary column, you see little beads that in between them you have little pores. So the pores that are in between these beads will allow the various gaseous molecules to interact with, and therefore this will also generate separation. Between these two types of capillary columns, the effectiveness is the same. So this is purely a design difference. So some column manufacturers manufacture their columns using the wall-coated method, and some manufacturers design their columns using the porous layer method. Both are equally good at generating separation, and therefore there isn't much difference between the two of them besides the design. Now, when we select columns or select stationary phase, there are several criteria that we have to consider. The first is thermal stability. Thermal stability is a given because we understand that these columns are placed in an oven that are typically run at temperatures between 150 degrees Celsius and about 300 degrees Celsius. So therefore, these columns must definitely be able to withstand these high temperatures. So you cannot have a column that breaks down or becomes reactive at these temperatures. So thermally, it must be stable. Chemical inertness. Now the insides of these columns, that polymer coating that we were talking about, the stationary phase, these must be inert, as they cannot start reacting with various gaseous molecules that are passing through the column. Right? So imagine if we inject a sample and the various chemical components start flowing through the column and start reacting with the inside of the column. Of course, that will certainly lead to disaster. So therefore, we do not want that to happen. So our columns, especially the insides of the columns, must be chemically inert. They must not react with anything that flows through the column. When we select the types of columns, we also want to select columns that are able to differentiate different chemical components, which means that they must have different extents of partition or different partition ratios for different chemical components. So for example, if you put in a sample mixture which has 3 components, A, B, and C, you want the column to interact with A, B, and C differently, to different extents. So that brings us to the point of different partition ratios, because if the column interacts with them in a similar fashion or to similar extents, then there's no way that we can generate a separation. So the interaction between the column with chemical A and chemical B and chemical C must be different, and only then can we get good separation. And of course, that extent of interaction is very dependent, earlier mentioned, on the solubility of these various components. The more soluble these components are, the more they'll interact with the stationary phase. The less soluble these components are, the less they'll interact with the stationary phase. And of course, this parameter is what allows us to separate the various components for detection. Now on this slide, we see a whole list of different types of columns or stationary phases, and these are paired with a whole range of applications for these specific columns or stationary phases. So I would first of all not recommend that we remember or memorize these different types of columns and their various applications. So this slide is mainly to show that there are different types of columns, and there are literally hundreds, if not thousands, of different columns and stationary phases with a whole range of different applications. But based on the criteria that we described in the slide previous, we should appreciate that for different applications, it is important for us to use different columns, and only then will we be able to generate good separation so that we can analyze each of our chemical components properly. So let's talk a little bit about film thickness of columns. So when a column is manufactured, we talked about it having a film of a coating on the inside of the column. So that film or that coating is actually the stationary phase that generates separation, because that's where the various gaseous molecules will interact with the stationary phase. Now, the thickness of that film varies from column to column. It can vary from a very low thickness, 0.1 micron, to a somewhat high thickness, 5 microns. So how do we decide what thickness of films to use when we want to use a column for a particular analysis? Well, this decision is mainly based on whether the chemical components that we are looking to analyze have high retention or low retention. So for example, if analytes have low retention, it means that they do not really like to interact with the stationary phase very much. So therefore, we may consider using a column with a thicker film so that we can encourage these components to interact a little bit more with the column, and therefore allow us to generate better separation. So of course, the opposite should be true. If we have analytes that are already very highly retained on the column, then we would try to use a column with a somewhat thinner film to reduce the retention time, so it doesn't take an incredible amount of time for the analysis to be complete. Now, sometimes when we need to analyze slightly larger analyte volumes, we may also consider a column with a thicker film. This is because with larger analyte volumes, the stationary phase or the film may be quite easily saturated, so therefore there is no room for the various gaseous molecules to interact with. So therefore we need a slightly thicker film that will give us more space for the gaseous molecules to interact with the film or the stationary phase. So earlier we did mention that if we have analytes with, by nature, very high retention, we would stick to columns that have somewhat thinner films. Now as we move towards the end of the instrument, the last component we're going to talk about is GC detectors. Now the detector's main purpose, as its name suggests, is to detect any chemical component that's leaving the column and to essentially draw us a peak so that we know that a certain component is present. We also mentioned that when this detector gives us a signal, the size of the signal or the size of the peak is actually proportional or indicative of the amount of the component present. So if we have a very large peak, that will tell us that the amount of that component in the sample mixture is very large. If we have a very small peak, that will tell us that the amount of that component in the sample mixture is actually very small. So we're going to discuss briefly three common types of GC detectors. The first is a thermal conductivity detector, the second is a flame ionization detector, and the third is a mass spectrometer. So as we begin our discussion on detectors, I would like you to pay attention to two things. The first is, for each detector, be roughly able to describe how each detector works, and to also pay attention to some of the advantages or disadvantages of each of these detectors. So the first one we'll be talking about is a thermal conductivity detector, TCD. So you'll see that this detector has two chambers, one on the left and one on the right, and it is contained within a heated block that is maintained at a constant temperature. So on the right, you see reference gas passing through, and on the left will be the gas from our column. So these two chambers constantly are filled with gas, and on the left we see the gas that's passing through from the analytical column, typically nitrogen or helium gas. So imagine if nitrogen gas is constantly filling the chamber on the left. Now nitrogen gas has a certain thermal conductivity, which means that it is by nature able to conduct heat a certain way, right? Which means that if over time only nitrogen gas is filling this chamber, then this filament, the wire filament in the left chamber, will be maintained at a constant temperature. But what if suddenly during our analysis we start to have different types of gas molecules eluting from the column and passing into the detector? So for example, you can imagine, what if ethanol gaseous molecules start passing into the chamber on the left? So if the chamber on the left is now filled with ethanol molecules, obviously ethanol has a different thermal conductivity from nitrogen, right? So it conducts heat differently from nitrogen. So therefore, what will happen to the filament in the left chamber? Its temperature will change because heat is being conducted now by ethanol molecules, no longer by nitrogen molecules. So as the temperature of this filament changes, we'll observe that the resistance of this filament varies with temperature. So when its resistance changes, the current passing through this wire also changes. So that is how this detector detects a change and tells us that yes, there is a strange chemical component now passing through the detector, right? It's not purely the carrier gas, which is nitrogen. So this verbalizes what we just described as gas of different types pass over the chamber where the heated filament wire is present. The temperature and therefore the resistance of that wire will change, and this is how the detector tells us that a certain chemical component is passing through the chamber, and therefore that leads us to obtain a peak on the chromatogram. Now, one of the key advantages of a thermal conductivity detector is that it is applicable to a wide range of chemical compounds. So you'll see it's simple, low cost, and responds to all substances. Response to all substances means that it is applicable to all types of different gaseous molecules. So it could be hexane or ethanol or propanol. Yes, it works for all of these. Just purely because all of these gaseous molecules will have somewhat different thermal conductivities, so therefore they will all be able to be detected using this detector. Now, the main issue with a thermal conductivity detector is that it is not very sensitive. So by nature, the differences in thermal conductivity between gaseous compounds, the differences are not that large. So it is a bit difficult to detect the difference in thermal conductivity between different gaseous molecules. So therefore, with very small concentrations of these gaseous chemical components, it will be very difficult to detect. So that leads us to the poor sensitivity point. So you do require that the concentration of these chemical components are somewhat on the high side for this detector to work. So it doesn't work very well for low concentrations. Now, the second detector that we're going to be discussing is a flame ionization detector. This flame ionization detector is by far the most common detector that is used with gas chromatography instruments. So we see at the bottom here, we have the carrier gas that's carrying the gaseous sample molecules through the column and to this flame. Now at this flame, clearly a combustion will occur, and a flame is also an energy source, so it will lead to the ionization of the gaseous molecules. Now once the gaseous molecules are converted to positive ions at the flame, they'll naturally be attracted to this negative electrode. So as they are attracted to the negative electrode and collide with the electrode, it leads to a change in the current of the circuit, and that is clearly detectable by the FID. So as more and more ions are generated and collide with the negatively charged electrode, that will indicate that there are quite a lot of that chemical component present, and if only a few ions are generated that collide with the negative electrode, that will indicate that only a small amount of these gaseous components are present. So the various components elute from the column and pass through a hydrogen air flame. The molecules essentially combust, break down, and are ionized. And the positively charged ions are immediately attracted to the negatively charged electrode. And once it collides with the electrode, it generates a current, and that current can then be measured as a signal and drawn as a peak on the chromatogram. So earlier I also mentioned that the amount of ions or the number of ions collected will give us an indication of the concentration or amount of that particular chemical component in the sample. If I have a large number of ions generated, that will mean that there are quite a lot or a high concentration of that particular chemical component. And if the ions generated are quite small, then that would mean that there's only a little bit of that chemical component present in the sample. Now the last detector that we'll be talking about is a mass spectrometer. So the mass spectrometer essentially detects gaseous molecules or gaseous ions based on the molecular weight or the molecular mass of these ions. So in the first diagram, we have a sample with your various gaseous molecules. As they pass through the mass spectrometer, the first thing the mass spectrometer does is convert these gaseous molecules to ions. So you see a whole bunch of positively charged ions. Now, since the molecular weights or the molecular masses of every gaseous component is different, the mass spectrometer is able to filter out the molecules of mass that we are not interested in and only retain the masses that we are interested in. So if in the beginning we tell the mass spectrometer that we are really only interested at ethanol molecules. Now ethanol molecules have a particular molecular weight or molecular mass, so the mass spectrometer is capable of retaining only the molecules or ions with that ethanol's molecular weight and filtering out the rest of the ions that are not interested. And essentially all the detector does is count how many ions of this particular molecular weight do we have. Clearly, if it counts a larger number of ions, it will indicate a greater concentration, and if it only counts a small number of ions, it will indicate a lower concentration. So what the mass spectrometer will give us is a chromatogram that looks something like that. So we actually have a line that indicates the signal intensity for each of the molecular masses. So for example, if we are looking at ethanol, then it will show, there will be a line showing up at ethanol's mass, and the height of that line will give us an indication of whether there's a lot of ethanol present in the sample, or is there just very little ethanol present in the sample. So again, here we have a list of a whole bunch of different types of detectors that can be coupled to a gas chromatography instrument, and there are some ranges in terms of its ability to detect, and there are also some applications on these detectors. I guess it would be important not for us to memorize these different detectors, but to understand that for different types of compounds, there are actually different types of detectors, and this is based essentially on the advantages and disadvantages that each of these detectors bring.